Hello guys, so welcome back to another video on lecture 9. Okay, and we're gonna continue discussing diode applications. In that particular, part of the lecture, we're gonna start discussing one of the most important applications of diode, which is diode clipping circuit. And as the name suggests, it clips. Yes, it cuts. So basically, you have a big input, big voltage with the input, and you're gonna take just part of it and clip or discard the other part, the remaining. That's basically clipping. Before we go into details in complicated clipping circuits with AC sources and stuff, we're gonna take a very simple example that will be our gate to clipping. So you may think it's not a clipping circuit, but it's a clipping circuit. And when we solve A, B, C, D, as we see here in the example, we're gonna discover at the end that this is basically a clipping circuit. Okay, so let's do that. So we have here a very simple example circuit. You have two batteries. One is called V input, one is called VB. VB is 1.4 volt. And the resistor here is 1 kilo ohm. As you just read here the example head. And says when VD on is 0.7, that means it forces you to use the constant voltage model. As I said before, you have three models, but 70-80% of the problems is gonna be solved using the constant voltage model. Okay. Let's start by A. This is A. Find the minimum input voltage, V input minimum, to turn the diode on as a function of VB and VD on. Good. So basically, it says to you that this diode will be only on when the input reaches some point, some voltage. For example, before solving, let's assume that this V input minimum, is 10 volt. That means when V input is less than 10 volt, the diode will be off. It will be open circuit. And once V input reaches this 10, the diode will be on. I mean, at V input equal to 10, the diode is on. 10.1 on, 11 on, 20 on, 100, whatever the value, as long as it's greater than 10 volt, the diode will be on. That's basically how you think about it when it says find the minimum input to turn. That means it's not on all the time. No, it's only on at certain voltage. When the input reaches certain voltage. Before that, when V input is less than V input minimum, the certain voltage, the diode is off. Good. To know this V input minimum, okay, let's check what is the point, the operating point of the diode at which the diode is, at the start of being on, let's say, which is basically the transition point. So here is, the clue. Just look at these characteristics here. Okay, this is the constant voltage model, guys. And here is VD on, which is 0.7 in that example. Okay, so this is basically the transition point, or the first point in the on region, or the last point in the off region. Okay, so basically when V input is equal to V input minimum, the diode will be working at that point. So at number A, at V input equal to V input minimum, the diode operating point will be at the transition point. Okay, if the diode is at the transition point, what would be V input and what would be VD and the ID? At the transition point, VD will be 0.7 or VD on, and the ID is 0 because it just started being on. Everything has a start. Okay, so this is basically very tricky because you may say, okay, ID is 0, so it's off. Look, it's just, you know, ended the off period and start the on period, or the on region. So just ending, because let's say that the input was increasing, but it is still less than the input minimum. So it's increasing all the time. It's less than the input minimum. The diode is off. Okay, VD is not 0.7, and the ID is equal to 0 until it reaches the transition point at the input minimum. At that point, VD will be 0.7 and ID will still be 0. But once we increase more the input, VD will be constant at 0.7 and I will start to increase in positive. Okay, that's basically, you know, it's a tricky part of that problem. Okay, so we know now at the transition point, we know that ID will be 0 and VD will be equal to 0.7. So let's locate that on the circuit. So this is the input minimum now, which we don't know. Here is I, or ID, because basically everything is series here. ID is just 0. VD is just 0.7. Can we solve the circuit? Yes, we can solve the circuit. Just apply KVL, just like this. So by KVL here, you can say that the input, which in that case, the input minimum, which is unknown, VR, you know, in that direction, because it's opposite to the current direction, plus or equal to. So the input is in that way. VR is opposite, VD is opposite, and VB is opposite. So the input minimum equal to VR, it's IR, VD is 0.7, VB is, so in that part here, just as a function of VB, so don't remove VB and put 1.4. It needs you to calculate the V input minimum as a function of VB. Okay, I is 0, so IR is basically 0, because 0 multiplied by R is just 0. So V input minimum equal to VB plus 0.7. That's basically the minimum input that we can put in order to, you know, make the diode to be on. And just let's think now before equations. Actually, we can get this value before even equations. I mean, without putting the equations and stuff. Just look at the circuit here. Just look. This is ground, so this is 0. And you have here a battery. This battery is called VB, 1.4 to whatever it is. It's of course in that case 1.4, but let's call it VB. Okay, that means the positive terminal of the battery is greater than the negative terminal by VB, by a voltage called VB. The negative terminal is 0, so this guy will be VB. Good. Now, Vn is equal to VB. The voltage at the N terminal of the diode is VB. And we know that when this guy become on, it must have a voltage difference equal to 0.7. I mean, VB, which is that point, minus Vn, VB, which is the B terminal, you know, minus VB, which is the N terminal now, equal to 0.7. So this point here must be greater than this point by 0.7. So it must be VB plus 0.7. So that the diode can conduct. Look at this. Look at this. Because basically, when the current is 0, okay, when the current is 0, so the voltage drop across the resistor will be 0. So that point will have a same voltage at that point. So at V input minimum, okay, the current is 0. So this is V input minimum. And this is VB plus 0.7. So this is basically the required value for V input in order to turn the diode on. Without equal, just by understanding, okay? And here is, of course, this is also understanding, you know, but in a more formal way. Okay, guys. So this is basically how to get V input minimum. Now let's continue our interesting stuff here. Number B. In B, we're gonna use now V input minimum. Find VD and ID if V input is equal to 0.5 and V input is equal to 2 voltage, 2 volt. So B. Number I, let's take V input equal to half a volt. Here you have two ways. You can start blindly, you just assume you have a circuit now. This battery is 1.4, which is VB. V input is, another battery with 0.5. Try to find if the diode is forward or reverse. As if you don't have, if you are not sure, just assume one assumption, then disprove or proof. All such stuff that we discussed before. But now, and this is valid, of course. But now you can do better because you know what is the input, what is the minimum input required to turn the diode on. So just now compare what you have with V input minimum. What we have now is that V input is equal to 0.5 and V input minimum is VB plus 0.7. So calculate first VB. So V input minimum. So V input minimum is equal to 1.4 plus 0.7. So this is equal to 2.1 volt. So that means we need at least 2.1 volt in order to turn the diode on. How about your current V input? Your current V input is 0.5, which is less than V input minimum. So since V input is less than V input minimum, which is the required value to turn the diode on, then the diode is off. So the diode here is off. And by the way, this is not assumption. I mean, now you are 100% sure that your diode is off. It's not assumption anymore because you know the conditions that will turn the diode off and you know the condition is not satisfied. So basically, if you start blindly without taking into consideration that you already know the input minimum, okay, and you try to assume on or off, if you assume on, your assumption will be incorrect. You will get something bad. I mean, a current negative or something. Okay, so something will be wrong in your solution. But now with that, we know for sure that the diode should be off. So I will leave that to you. Just assume it's on, okay, and you will find something wrong, and you will know that if it's not on, then it's off at 0.5. Okay, if the input is 0.5, it's less than the input minimum, diode is off. So ID, one of our unknowns, is 0 for sure. Now VD by KVL, V input equal to IR, I times R, plus VD, which is unknown now, plus VB, which is 1.4. So this is equal to V input is 0.5, I is 0, 0 multiplied by anything is just 0. VD is unknown, VB is 1.4. So VD is 0.5 minus 1.4, so it is minus 0.9 volt. That means it was reverse. That means it was reverse. It was really off. That's just a proof that it's off. So it's here, basically. For example, here. This is for example minus sketch minus 0.9 volt, which it's negative. So that is really off. Now, how about if V input is 3? This is number 2. 3 volt. So now this guy will be 3. Again, compare it with V input minimum. V input minimum, we just calculated it in number 1. It's 1.4 plus 0.7. It is 2.1. So 3 is bigger than or greater than 2.1. So since the input is greater than the input minimum, the diode is on. And since it's on, then one of the unknowns is known now, which is VD in that case. So VD is 0.7 or VD on. Look, if it's off, you know one of the unknowns, ID. Then you calculate VD from the circuit. If it's on, you know VD, and then you calculate ID from the circuit. Good, so let's continue. We now know VD, but we don't know ID because it's one of the unknowns. So again, Kershaw Voltage Law. So from Kershaw Voltage Law, the input, which is 3 volt, equal to R is 1 kilo ohm, plus VD, which is 0.7, plus VB, which is 1.4. So I is equal to 3 minus 2.1 over 1 kilo ohm. This is basically 0.9 milliamperes. Positive, and it must be positive because you didn't assume, you know, it should be forward, you know, and on. Okay, that's very nice. Now let's continue with something more interesting now, which is sketch the transfer characteristic of that circuit, the output versus the input. Okay, this is really interesting, you know. Okay, so in A and B, we were calculating VD and ID, you know. But now it wants you to calculate or to draw the output versus the input. And he calls that transfer characteristic. So you should learn that new terminology if it's new for you. That whenever you hear transfer characteristic, so basically we mean a relation between something in the output to something in the input. Here we consider the voltage across VB and VD, the output, and the voltage across the input, which is the input, is our input. And we want to sketch the output versus the input. I mean, on the vertical axis you have VO, the horizontal axis you have the input. And this is just a sketch, you know. So here we have a clue how to deal with such a situation. So let's say C here. So we know that the input minimum, which is 2.1, okay, or VB plus VD on, in a more general, you know, term. We know at that point the diode will start to conduct, will be on. So let's check, you know, make some checks here. You know, we'll take just, you know, three values for with the input greater than or equal to the input minimum, and some other 3 values less than the input minimum. Let's check how the output will be in both cases. Okay, so let's divide, you know, the screen in 2 halves. So let's take examples for the input greater than the input minimum. Okay. Basically, before that, what is VO? So if you look at the circuit here, if we take KVL in that loop at the output, you find that VO is just VB plus VD. So VO, all the time, it's equal to VB plus VD. Or 1.4, you know, if you want to make it more specific, plus VD. Okay. What happened if the input is greater than the input? Let's take some examples. Let's take, for example, the input equal to 3, the input equal to 5, the input equal to whatever, 100. You know, any value is greater than the input minimum. When the input is equal to the input, when the input is equal to 3, we just saw it here in number 2, B2. We see that the diode is on because the input is greater than the input minimum. Okay, and VD is 0.7. So here the diode is on. Let's write it. Diode
is on. So VD is equal to 0.7. So just compensate here. So here, so VO will be equal to 1.4 plus 0.7, which is 2.1 volt. Good. How about 5? If the input is equal to 5. If the input is equal to 5, again 5 is greater than 2.1, which is the input minimum. So the diode will be on. If diode is on, then basically it has VD equal to 0.7. So the output again, which is VO plus VB plus VD is equal to 1.4 plus 0.7, again 2.1 volt. What if the input is equal to 100? Again, the input is 100 greater than 2.1, greater than the input minimum, so that is on. So VD again is equal to 0.7. Remember, whenever the diode is on, according to the constant voltage model, VD is equal to 0.7. So again, VO is equal to 1.4 plus 0.7. What we learn from here? Basically, whenever the input is greater than or equal the input minimum, VO is constant equal to 2.7. Or in general, VB plus VD. So let's now do the second part, in which the input is less than the input minimum. Okay. I'm gonna write first the Kershaw Voltage Law. So here is from Kershaw Voltage Law. We write this equation 2 times. One when V input is equal to half, and then when V input is equal to 3. It's the same equation, in which the input equal to VR plus VD plus VB. Good. When V input less than V input minimum, which is 2.1, I mean when V input is equal to 1, 0.3, minus 6, minus 7, minus 100, any value less than the input minimum, the diode will be off, whatever the value is. So when the diode is off, I will be 0. So VR, which is I times R, will be 0 as well, whenever the input is less than the input minimum. So the input will be VD plus VB. And what is VD plus VB? It is basically the output. So, as a rule, when the input is less than the input minimum, the output plus equal to the input. So we have here 2 equations. One says, when the input is greater than the input minimum, the output is equal to 2.7. And when the input is less than the input minimum, the output is equal to the input. So let's draw that. Let's sketch that. Here is basically the sketch, but I want to show you how to do it, by yourself. So I'm gonna make 2 axes like this. Here is VO, and here is the input. Let's do it with another color. So in the beginning, when the input greater than the input minimum, the output is equal to VB plus VD. In general, in a specific case, in our case here, VB is 1.4, VD is 0.7. This will be 2.1 volt. And when the input is less than the input minimum, diode will be off, the output is equal to the input. Good. Now we're gonna assume that that this is, for example, the input minimum, which is 2.1. Just a sketch. It is just a sketch. So for any value greater than the input minimum, which is, for example, this value or this value, or all these values here on the axis is greater than 2.1 or the input minimum. What would be the output in that case? The output will be 2.1 or VB plus VD. So let's assume this is, for example, this point. This is V input. This is basically, I'm sorry, VB plus VD, which is 2.1 volt, constant. So that's basically when V input is greater than V input minimum. How about when V input is less than V input minimum? So V output is equal to V input. What does that mean? When V input, for example, is 1, V output will be 1. When V input is 0, the output will be 0. When V input is -1, the output will be -1. When V input is -2, the output will be -2. So it's basically a linear line crossing the 0, okay, with a slope equal to 1. And let's now here take a short look. What is this? This is basically a clipping. Why? Because whenever we increase than the input minimum, the output is constant. The output is clipped. Okay, so here, that's basically whenever the input is greater than the input minimum, the output is constant. So before the input minimum, the output is equal to the input. And I mean, just the following, you know, so -2, -2, -1, -1, -half, -half, 0, 0, you know, 1, 1, 2, 2, 2.1, 2.1, then it doesn't follow anymore. When the input is greater than the input minimum, 2.1, it clips. It stops at the input minimum, or 2.1, and become constant, you know, until infinity. That's basically clipping. Okay. So in the next video, I'm gonna show you a very good example for this. I mean, practical example which we use in our daily life. Then we're gonna take or study more complicated circuit for clipping. So see you in the next video. Bye bye.